Good morning, ladies and gentlemen. Today we start the lecture 12, characteristics and performance of transmission lines continued. We have seen yesterday how the change of excitation controls the power factor and the current. Now, as you can see in this diagram, three diagrams are drawn. As you can see very clearly, the voltage, terminal voltage remains constant. This is the phasor. OVT, OVT, OVT remains constant in all the three. The current in figure A is lagging by angle theta. Current in figure B is in phase with the voltage, and current in figure C is leading, right. Now, as you know the rules of the game, that is drawing the phasor diagram, you have to add to the V the reactance drop. Resistance is neglected, and this is to be added at 90 degrees to the current. So, naturally this is the, if you proceed further, this is 90 degree, and this is J I A X A. So, you get E F, and the angle between V and E is called torque angle, load angle, which is always shown by delta. This is called overexcited case. The E is much higher than VT. It is an overexcited case. Normal excitation is when the current and voltage are in phase. It is a unity power factor. This was lagging, unity, and you have to just add 90 degree, and this is EF, which is definitely lower than the case B, case A, and this is normal excitation. It is called normal excitation. And the case C, which is under excited case, the current is leading by angle theta to the voltage V. You add the drop, and EF is very small, in fact smaller than the V. So, you can see how beautifully we have controlled the power factor from lagging to unity to leading just by changing the excitation. And there are various methods of excitation control available in the literature, and that is the beauty of synchronous machine, that it can be operated from this. You must have done in your practicals in undergraduate, V curves synchronous machine. So, you can operate the machine from lagging to unity power factor to leading, which is not possible in induction machine or any other machine. So, that is why it is versatile machine, and it can supply negative watts, positive watts, or anything. This is the well known power angle curve, P versus delta. Okay. This is y axis is real power, x axis is delta. This is for generator operation, this is for motor operation, and in fact this is the P max. Here also it is P max, which is delta is equal to 90 degree. and this is a well known equation for real power or active power generated, EF Vt upon Xs into sin delta. If you reduce Xs, P goes up, and that is why we are using bundle conductor where Xs is reduced. That is why we are using parallel lines, because if there are parallel lines, the X will be less than the individual line. Parallel lines incidentally also gives you reliability, because both the lines failing, like both kidneys failure, is very rare and very unfortunate if somebody has both the kidneys gone. If you increase the voltage, again the power transmission is increased. That is why you go for 400 kV, 800 kV, 765 kV. So, this picture gives you a clear picture how power is controlled, and the controlling factor are reactance, the power angle, and of course, the voltage. You can see why this is called stable. If it operates from here to here, this is stable region, and this is unstable. Why? Can anybody reply this question? Why 0 to 90 degrees is stable and 90 to 180 degrees is unstable? Because here the delta goes up, that means speed goes up, the power also goes up. So, this is a positive, tangent is positive, whereas reverse happens from 90 degree to 180 degree, the speed goes up, power goes down, which is not, like your expenses go up, your salary or your income should go up. If not, it is unsustainable situation. You will have to either have to go take loan, or you have to cut short your other expenses. That means you will be faced with a problem. If your expenses go up and correspondingly income does not follow up, then you are having a same thing happens in electric machine. If delta goes up and power comes down, it is unstable. Of course, stability is a separate chapter altogether, which we will be doing next semester, ESL 860, power system analysis. Now, this is a salient pole synchronous machine. The air gap is not uniform. I have drawn the picture yesterday. So, what happens? There are two reactances, direct axis and quadratic axis, and XD is more than XQ. Okay. Do you know what is the normal value of XS now? It is now going up to 2 per unit. It is on increase, and air gap is almost reduced to irreducible value. You can't further reduce the air gap, because the rotor has to move. If there is no air gap, it cannot be 0. The trend is that SCR ratios has a coming down, because SCR is inverse of XS, short circuit ratio, SCR, not silicon controlled rectifier. SCR has so many other meanings also, right. So, short circuit ratio is inversely proportional to XS. Yes.
JXQ will be the next IAXQ, JIAXQ.
Here you are talking?
Yeah. So
no, we will come to that. We have not yet started the phasor diagram. I am only telling you the fundamentals of it. The values of XS is gone up to 2 per unit. It is going up and up because we want to reduce SCR. That is the norm, because the sizes are coming down and down, machines are becoming compact. the air gap is reduced, naturally the x will go up. Now, xd is more than x cube. If it is 0.8 per unit, it is 0.6 per unit, something like that. Now, we come to the phasor diagram. This Vt is horizontal, it may not look so in figure, it is a reference phasor. This is the current, the resistance has to be added, the resistance drop in parallel to the current which has been done, and then this should be 90 degrees to this. Obviously, the diagram has not been properly drawn. I think we can draw it properly. Of course, it is not to the scale. Draw this. It is very simple way of drawing diagram. Draw parallel to this, perpendicular, and this is your E. And this is your, the whole thing is IA XD. Is it okay or not? Is it not the same thing? But now it is okay. This part is okay. Okay, this is not 90 degrees to this. This is going somewhere outside the paper. So I think this diagram is okay. All right. And this is the easiest way to draw a. This is a two reaction theory. Where do you use this salient pole machine? Any idea? Hydropower plant, because their speeds are low. So you need the salient pole machine in hydropower plants, and you need cylindrical rotor machine in thermal power plant, because their speed is 3000 rpm and so. Okay, so we were talking about the two reaction theory, which is in fact required whenever there is a salient pole synchronous machine. Why? Because the air gap is not uniform, and once air gap is not uniform, the machine presents two types of reactances. One which is along with the direct axis is called direct axis reactance, another which is quadrature to that, quadrature means 90 degree, is called quadrature axis reactance, xq. xd is always more than xq, and when it becomes equal, that means the machine is reduced to cylindrical rotor synchronous machine. Now, we have seen here the phasor diagram for salient pole machine, and that I have already explained you. Let us now go for the power angle curve for the salient pole machine. As you can see, this part was known to us for a cylindrical rotor, and this part is called reluctance power, which is a second order term. That means there has to be a more power in salient pole machine, and so the maximum also shifts slightly less than 90 degrees. All right. So we superimpose the sinusoidal term with the second order term, and you get this dotted curve as a P maximum, which is higher than the P maximum of cylindrical rotor machine. So you get extra power. In fact, there has been machine design based on this principle called reluctance motor, which runs on only reluctance power, which you might have read in machines course. Otherwise, you can see our machine book or any book. Someone asked last time what is representation of loads. So now the time has come to talk about load modeling. This is also called load modeling. And as I said, it is a very important topic. You can do in fact PhD. There are books on load modeling. Load toughest parameter to assess. because it is a random variable. When it is going to rain, nobody knows. People do forecast, but it may go wrong. In fact, you are aware of normal distribution or Gaussian distribution, which is like this: minus 3 sigma to plus 3 sigma. Sigma is standard deviation. This is the expected value. I don't know whether you have read it in your probability theory or somewhere. This is called normal distribution or Gaussian distribution. So, variation is around the expected value or mean value, and that is why load, anything which is random variable. When you will get a phone call, nobody knows. You only have phone in front of you, and any time it can ring. When the customer will come in the shop, nobody knows. He never announces, he never gives you notice. When the death comes, nobody knows. It is also a random variable. Even the birth is a random variable, exact time of arrival. That is why it is called expected time of arrival, ETD. They count some 9 months or whatever, but it always go 15 days this way or that way. So, load is a random variable, hence it is very tough to assess. Load forecasting is there, statistical methods are there. You have the the extrapolation technique. For example, as I had shown you, up to 2003, whatever is the earlier curve, we can always say 4 it likely to be this value, but things may go wrong. It may not happen, the monsoon may fail, the summer may be severe. So, you need more AC load, and which you have counted on some basis, and that basis is no more there. So, that is why it is called random variable. The whole design and operation of power systems depend on load, both economically and electrically. It is influenced by nature and magnitude of loads. If load is there, then only we generate. If there is no load, why should we generate? We are not generating power in Satpura jungle or somewhere where there is nobody, there is no industry, there is no living being. Roughly, the percentage of various loads are given here. Industrial motors vary from 55 to 75. If it is a region of Vidarbha, underdeveloped, Jharkhand, Bihar, no industries, then the industrial motors used are 55%. But if it is Bombay, Pune, Bangalore, Hyderabad, it may be as Delhi, it may be as high as 75%. So is synchronous motors, it varies from 5 to 15%. The electric clocks use synchronous motors. The paper industry uses synchronous motors. Why? Because you need a constant speed motor, and synchronous motor is the only motor which, if it runs on synchronous speed, otherwise it does not run, 0. A newspaper cannot be, a first page will be different width than second page, then third page, you will feel awkward. A book, all pages are supposedly uniform. A copy where you are taking notes, each page must be same size, same thickness, same height, otherwise the copies will look very odd. Lighting and heating is remaining 20 to 30%. Heating in our country is not so much, because we hardly have a winter. Winter is confined to few hilly areas, north areas, Himachal Pradesh, Jammu, Kashmir. Even you must have seen Srinagar temperatures this time 30 degree. So, it is also global warming. But lighting, 5-star hotels for example, 40% of electricity bill is because of lighting. Studios, you can see the amount of illumination level is very high. Shops, monuments, you need a good lighting. Tennis court, the day and night match, so lighting levels will be very, very high. As I told you, there are 3 ways to represent the load. Constant power representation, right. For example, in load flow, you have megawatt and MVA are constant. Constant current representation, which is required in protection, P minus JQ by V star, I magnitude delta minus theta. V is equal to V angle delta. Theta is tan inverse Q by P. Magnitude is constant. And the third is constant impedance representation or admittance, that is one and the same thing. They are inverse of each other. Z is equal to 1 over Y, or if it is a matrix, Z is equal to Y inverse. V by I, we have just found out the value of I, V squared by P minus JQ, 1 over Y. So, this is a constant impedance, a load of 5 ohms, right. So, these are the three ways in which you can represent load: constant megawatt, constant current, and constant impedance or admittance. Now, we are starting chapter 5, performance and characteristics of transmission line. Why do you want to study this? This is a proper transmission line now we are going to study. Because we need to worry about flow of P and Q on lines. How much real power is flowing? How much reactive power is flowing? What are the various values of voltages on nodes within limits? It has to be within limits. What are the limits? 0.95 per unit, 1.05 per unit. This is the limit. You can't vary voltage beyond this, lower than 0.95 or higher than 1.05, 5%. Voltage is supposed to be constant. Performance of a single transmission line we will study, because it is easy, because principles are same, whether it is a single, whether it is a double or anything. We will consider balanced 3-phase load, because most of the time loads are balanced. That is why you will see in domestic supply they use all the 3 phases such that the loads are balanced. Analysis is always done on per phase basis, even in industry. And 2-port network, it is, you must have done the circuit theory, there you must have read 2-port network, which are solved by H parameters, Y parameters, Z parameters, G, so on. This you must have done in your circuit theory. This equation is very important. This is the crux of the matter. What does this equation show? It shows how a sending end is connected to receiving end. The subscript S denotes sending end, subscript R denotes receiving end. Receiving end is normally load end, sending end is normally generator end, at least for an isolated system. If it is a interconnected power system, as I have been repeatedly telling you earlier, from any end you can send power, from any end you can receive. In fact, from the end you are sending power, you can also receive power. India gets aid from various developed countries. We also give aid to Nepal, Bhutan, Bangladesh, the countries which are poorer than us. So, we definitely have a give and take. This identity is very important. AD minus BC is equal to 1. Why it is very important? If you know 3 constants, you can find out 4th one without actually conducting an experiment. A, B, C, D, these are the 4 generalized circuit constants, or they are also known as ABCD constants. Please read appendix B of the book to determine these constants. How to find out, how to determine in lab. So, that is given in detail. I am sure you must have done it earlier also, but if you haven't, then kindly go and read the appendix B. Am I right? Is it in appendix B? Yeah. So, please read any book, whether it is a red book or brown book or green book or blue book, and now black book is coming Monday, the 3rd edition. So, you can find this appendix in all the variations. From here it should be clear to you, how do you find out A? The A can be found out, which is as simple as that. Let us write the whole equation. Vs is equal to AVR plus BIR. So, A will be equal to Vs upon VR with IR is equal to 0. When you say IR is equal to 0 is what? Open circuit. Absolutely, very good. The receiving end is open circuit. Now, I have been telling you repeatedly, the voltages most of the nodes remain same or nearly same, because as it is they are allowed to vary between very narrow range, 0.95 per unit to 1.05 per unit. That gives you immediately a clue. The value of A has got to be around 1, because Vs and VR are roughly same. So, the value of A is nearly 1, and the angle will be very small, because A is a phasor quantity. So, the angle will be around 0 degree, maybe 5 degrees. So, when you do a numerical, and if you happen to get the value of A as 958, immediately bell should ring in your ears that there is something has gone wrong drastically. And if you do not have a time in any exam to correct such situation where you are sure that you have gone wrong, please write a note to examiner, sir, I know the value of A should be around 1, however, I have gone somewhere wrong. He will give you some credit that at least you know, you are aware that A should not have been 958 or 18 or whatever, it should have been nearly 1. How about B? The B from here can be written as Vs upon IR, where VR is 0. So, that means the receiving end is short circuited. Can you tell me the units of B? Ohms. It is an impedance, whereas A was dimensionless. There was no units to A. If I ask you this question in UPSC or anywhere in TPC, what is the unit of A, generalized circuit constant? You should not say ohms or mhos or something. It is unit. There is no unit. It is dimensionless. B is nothing but impedance, the transmission line impedance, and its units are ohms. Now, we come to C and D. Is is equal to C times VR plus D times IR. And if you want to calculate C, Is over VR, that means receiving end is open circuit. And please remember, the dimension of C or units of C will be, nowadays it is called Siemens, or if you want you can write mhos. And finally, the value of D receiving end short circuit. Please understand, the value of D is again dimensionless, current upon current. And in fact, these currents are very nearly equal. If you consider the short line model, there is no shunt parameter, series circuit. So, whatever is 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 equal to IR. So, D becomes 1. A also becomes 1. If it is exactly same, the voltages are 1 per unit, and that is called flat voltage start. When all the voltages are 1 per unit in a system, the system has a flat voltage start, same 1 per unit holds. Angle will be different, otherwise there will be no power transfer. If the angles are also same, the magnitudes are also same, then where do you think power will go? Nowhere. It cannot flow. Now, all the 4 constants, as I told you earlier, need not be computed, because there is an identity which links all the 4 constants, and that identity is AD minus BC is equal to 1. So, having computed 3, you can calculate 4th. Further, for special networks, A is equal to D, which are bilateral and all those in there. Otherwise, A will be different than D. What is a short transmission line? There are 3 types of transmission lines. What are those 3 transmission lines? Short, very good, medium and long. From Delhi to Panipat, around less than 100 kilometers or around 100 kilometers, it is a short transmission line. From here to Ambala, it is a medium transmission line, and from Delhi to Nagpur, long transmission line. Why you want to divide transmission line into short, medium and long? Their characteristics change, their performance change. Even a layman will know that when you want to carry a large amount of sum, you take a draft. But if you are going for KLS for drinking cup of tea, you won't take your bank card or ATM card or checkbook, 2 rupees, you take cash. So, short line, medium line, long line, all the 3 lines models are different, characteristics are different, performance are different, and that is why we have divided the line performance into 3 parts: short, medium, long. We start with short. As I have just explained you, it is less than 100 kilometers. Less than 100 kilometers. 50 hertz shunt admittance j omega C L. L is the length of the line. Is neglected. There is hardly any capacitance. And so, the model is, short line model is simple series circuit, shown in the next slide. This figure is the simplest type of figure for a transmission line. You cannot get a simpler figure than this. There is a sending end, there is a receiving end, and this is the line. This is sending end voltage, this is sending end current, which is same as receiving end current. This is receiving end current. This is a load. This is a load voltage or receiving end voltage. The line is modeled by just series impedance R plus jx. All right. So, what will be the ABCD constants for such a line? It will be A will be 1, D will be 1 and C will be 0
B equal to Z.
and B will be Z. Okay. Why C is 0? Because Is is equal to Ir. Why A will be 1? Because Vs is only the drop plus Vr. Let us write the equation. These are the equations. Vs Is 1 0 Z1 Vr Ir. I can write Vs in this particular form: Vr cosine phi r plus Ir whole squared plus Vr sin phi r plus Ix whole square. Now, you may ask me from where you have got this equation. This equation is coming from this diagram. This is origin, this is Vr, this is the current, which is same as Is equal to Ir. Okay. This is receiving end power factor, this is sending end power factor. You add this Vr, the resistor drop, add reactance drop, and this is nothing but Iz, and this is Vs. Now, how do you get the value of Vs in terms of Vr? Consider this triangle you must have done in 9th class, Pythagoras theorem. It used to be theorem number 29 in my days. 1958 I learned that Pythagoras theorem. What was Pythagoras theorem? The square of two sides when added gives you the square of the hypotenuse. A square plus B square is equal to C square. C is hypotenuse, A and B are two other sides of a right angle triangle. This is a right angle triangle, this is 90 degrees. So, O, A, B. I am interested in getting OA. So, OA is Vs. So, OA square is equal to this square plus this square. What is this? Vr cosine phi r are this part, and this Ir is as it is Ir, and what is this part? Ix, and what is this part? Vr sin phi r. So, now I hope you will have no objection in accepting this equation as Vr. Vr cosine phi r Ir whole squared plus Vr sin phi r Is whole squared under root, otherwise Vs squared. So, this is nothing but Pythagoras theorem. You do not know when you use what. What you learned in nursery you continue to use whole life. 3 plus 2 is equal to 5. When you take sabji, when you take something, you add. In US you will be surprised, even that they do by calculator. They are not able to add 13 plus 8 is 21. Is it 38 plus 21? $21 please. Something like that. Whereas our mathematics used to be very strong. In our days we have used even the table of factors of sawa, deda, dhai, we could have said 7 dhais are. So, it used to be 17.5. You may take so much time to find out 7 into 2.5. Anyway, rearranging the terms. Who knows, tomorrow you may also write book, some of you. So, you have to write that term here. Here language is not there, because we have to economize on the slides also, time also. So, Vr squared from here, because cosine squared phi r plus sine squared phi r is 1. Trigonometry, I do not know which class you have read, I read it in 11th class. So, trigonometry by Loney, right? Loney's books are famous for last 100 years. Still, his great grandsons are also getting royalty. So, V cosine squared phi r plus sine squared phi r is 1. So, this Vr squared plus I squared r squared plus x squared twice Vr I r cosine phi r plus x sin phi r under root. This is the equation for Vs. Of course, you can check it from book or from anywhere. Further simplifying, I do not think you can copy it, maybe you can take it from the book. It is as it is given in the book, so you do not have to copy, just understand what I am talking. Now, I am simplifying. What I am simplifying? I am ignoring higher order terms, neglecting higher order terms. Now, I am putting the sign of approximation, or VR 1 plus IR VR cosine phi r, IX VR sin phi r. Finally, this is what you have to remember, whether it is a machine or it is a power system. This is called CTM. What is CTM? Commit to memory, because most of the problems are solved using this formula, that Vs is equal to VR plus I R cosine phi r plus X sin phi r. This is the drop across the line, this is the receiving end voltage, this is sending end voltage. So, we have derived it using a phasor diagram, using mathematics, Pythagoras theorem, Taylor series expansion, in fact we have used, and ignoring higher order terms. Finally, we have got this equation. So, this equation is very important. The diagram I have shown you is a phasor diagram I have just now shown you of a short line for lagging current. If it is leading current, diagram will change, still same Pythagoras theorem, same mathematics. What will be the change? Instead of plus, you will get minus. Not here, sorry, here. Instead of plus, you will get plus, minus here. That will be the only change. So, when I ask you to derive the equation for a leading power factor, for God's sake, do not derive for lagging and then change the sign, you get 0. You have to derive for leading only. Only answer is this, that does not mean you derive for lagging and then say okay, for leading it will be minus 0 straight away. What is voltage regulation? I think we will do voltage regulation tomorrow. So, any questions you have, whatever we have done today? What we have done? We have done the excitation control, how to change the power factor angle, how to change the value of current, keeping the active power still the same, so that the constant V I cosine theta remains the same. So, we have seen overexcited case, we have seen a normal excitation case, we have seen under excited case. Then we have seen synchronous machine, the two reaction theory, salient pole, power angle diagram, how the P max is more than the P max for the cylindrical rotor, thanks to the reluctance power. We have also seen the reluctance power can be used for a new variety of machine called reluctance machine. Then we have seen the most important parameter in the whole electrical engineering, but for which electrical engineering won't have been there, load modeling. There are books, there are papers on load modeling. The best paper is by Talukdar, load management, I told you earlier also. Then there is a constant megawatt or MVAR, constant impedance, constant admittance and constant current. Depending on the particular study, you are going to use the load modeling, corresponding load modeling use. There are still sophisticated models, like with voltage variation, load also varies. Like when you have to go walk a furlong, you walk. If you want to go to a mile, you may take your cycle. If you want to go for 2 miles or 2 kilometers, take a scooter. If you want to go to 30-40 miles or kilometers. You have a car, you take a car. So depending on the requirement, you change your mode of transport. If you have no money, then you go for bus. If you still those are, even if that bus money is not with you, then you take lift. But taking lift is very dangerous nowadays. All of you know that. So depending on requirement, the modeling changes. Okay. What is your objective function for modeling? Yeah. Any other question? In fact, you have not asked any question. I was explaining. If not, then please read further, and tomorrow we'll talk on medium line modeling.